So today's video topic will be linear approximation. So we've seen in previous units and in previous videos that a tangent line of a curve is a very close approximation of that curve when you stay near where it's tangent. So in other words, at the point where the tangent line hits the curve, sections right around there, the tangent line's y values are pretty close to the curve's y values. But as you get further away, it's not as good of a representation. So in fact, if you have some curve, if you just keep zooming in, so if you look at the screens on the right, the window keeps zooming in further and further. So if you zoom in far enough, it actually starts to appear somewhat linear when you zoom in far enough, which is why a tangent line at a certain point can be used as an approximation when you're really close to that point. So the idea of this is that sometimes you might not be able to find other y values near a given point. At one point it might be easy, but really close to it might be kind of hard. So you might not be able to find those y values given your curve. But if you know the tangent line, you can use your tangent line to at least approximate those y values. So we will try and find the linear approximation of a curve to help find y values that are nearby y values that we already know. So in general, what we'll do is we'll use point-slope form. Our point-slope form we usually see is y minus y1 equals our slope times x minus x1. Well, here they're just saying your y here. They're calling f of a your y1. F prime of a is just your slope at that point, and a is the x value that you're working with. But this is really, all we're just really doing is point-slope. So we want basically to find a function that approximates our function very close to some point. And that's called the linear approximation. The book likes to use L of x to represent that. So basically what we'll do is we'll do y minus y1 equals our slope times x minus x1. We'll be able to plug in for everything except for y, and we'll add the y over to the other side. So that'll give us y is equal to y1 plus the slope times x minus x1. Okay, that's essentially what we have here. They're calling our plain old y L of x, okay, as a function of x. Our f of a is just the y1. F prime of a, that's the derivative. We know the derivative at a single point is just our slope value. And then we have x minus our x value. So it's really this is just point slope that we're going to do. So what we'll do first off is see if we can approximate square root of 3.98. Well, square root of 3.98, that's kind of tricky to figure out just from that function. And we're going to think of it as square root of x plus 3 to help approximate it. Well, first thing you want to do is determine an x value that's nice nearby. So we're going to say a equals 1. Because when we put 1 in, it'll give us something nice back. So this is going to give us our point we'll work with. When we plug in 1 for x, we'll get back square root of 4, which is just 2. So that's a really nice point. So that's the point we'll work with. And then we'll find what is f prime of x. Well, when you take the derivative, 1/2 will come out front. You'll have x plus 3 to the negative 1/2. Well, that's the same as saying 1 over 2 square root of x plus 3. We're now going to find our slope. We want to find f prime, again, when x is equal to 1 in our function. When we do that, that'll give us 1 over 2 square root of 1 plus 3. Well, 1 plus 3 is 4. Square root of 4 is 2. 2 times 2 is 4, so this will just end up giving us a slope of 1/4. What this does is it allows us to do point-slope form now. We will have y minus our y value of 2 equals our slope 1/4 times x minus our x value of 1. Distributing the 1/4, we get y minus 2 equals 1/4 x minus 1/4. And adding the 2 over, 2 is the same as saying 8/4. So we'll have 1/4 x, negative 1/4 plus 8/4 will give us 7/4. Now the book, you might see them instead of y, they might have L of x. I am okay with either, however you would like to express it. What this is our equation of our line that is tangent at the point 1, 2. Rather than using our function square root of x plus 3, we can use this line to approximate values really close to when a is 1. So we'll now start out and see if we can find square root of 3.98. In order to find that, we need to think about, well, what value are we really putting in for x up here? To get 3.98, we really want to put 0.98 in place of x. So in our function here, we'll do L of 0.98. And that will tell us what our y value is as an approximation. When we do that, we get back 1.995. So what this is saying is an approximate value of the square root of 3.98 is about 1.995. Now the other one we wanted to do was square root of 4.04. Well, the x value that we would need to get 4.04 into the radical is 1.05. So we're going to do L of 1.05. Again, we'll just put 1.05 in for x. And what this does is this gives us an approximation of what square root of 4.05 really is equal to. When we plug those in, we should end up getting 2.0125. Now, these are not the exact values of square root of 3.98 and 4.05, but they are approximately what they are. And doing this is a lot easier than actually figuring out, well, what is square root of 3.98? Or what is square root of 4.05? Now, we want to know, are these overestimates or underestimates? Well, we're working with a square root graph. Okay, square root graphs look something like that. We were doing the tangent line at the point 1, 2. So right here. Our tangent line is slightly above the curve. Because it is above the curve, these would be overestimates. If we had had something like this and had a tangent line, then our tangent line approximations would be considered underestimates. But because we are above the curve with our tangent line, it makes these overestimates. Okay, and here's just another visual example of that. That red line there, it's a little bit above the curve, so what we found, they were slightly overestimates. Now, just so you can see compared to the actual values, here's square root of 3.98. This is what we got. This is the actual value. So notice it's pretty close. And here's square root of 4.05. We got 2.0125. It's actually this, which is pretty close. Now notice as long as we stay pretty close to 1, those values of L of x are pretty close. As we start moving further away, like if we get all the way down to 3, now those are not as good of approximations. So as long as you stay close to the point where it's tangent, the line can be a good approximation of your y values of the actual curve. As you move further away, it is not necessarily as good of an approximation. So let's see if we can approximate square root of 26. The difference with this one is they don't give us the function to work with. So we need to decide what function we're going to do. What you want to do is just, if it's a radical, just make it radical x. And then what you'll do is you'll pick a nice x value that is close to what you want. We want 26. The nicest x value close to 26 would be 25, because square root of 25 comes out nice. Our y value when we plug in 25 would be 5. Well, look, we already got our point. We got our x comma y. We'll now take the derivative. This will be 1/2 x to the minus 1/2, because square root is really like raising it to the 1/2. If we rewrite it, it's a little easier to work with. So this is 1 over 2 square root of x. We'll put in our 25 to get an actual numeric value for our slope. Square root of 25 is 5. 5 times 2 is 10. So this will give us that our slope is 1/10. So doing point slope now, y minus y1 equals our slope times x minus x1. We'll have y minus 5 equals 1/10 times x minus 25. So if you get y by itself, this would be 1/10 times x minus 25 plus 5. Again, I'm fine if you leave it as y. The book might show it as L of x. Either is fine in my book. And all we do now is plug in the actual x value we wanted. We wanted x to be 26 in this case. So we'll have y equals 1 over 10 times 26 minus 25 plus 5. 26 minus 25 will give us 1. 1 times a tenth is just a tenth. So y is really equal to 5.1. What this is saying is we are approximately at 5.1 when we do square root of 26. Now, we might want to know sometimes our linear approximation, how good of an approximation is it? So thinking back to our first example, we were approximating the function square root of x plus 3, and our linear equation we got was 7/4 plus 1/4 x, or x over 4. Well, what if we said we only wanted to use our approximations if they stayed within 0.5? Or in other words, if it goes beyond 0.5, we're saying, well, it's not a good approximation anymore. Well, what we can do is we can find the x values where that would hold true. So what we'll do is we're going to go to the calculator. What we really want to know is we want to know when is the difference between our actual value, so square root of x plus 3, minus the y values of our function, x over 4 plus 7/4, our linear function that is. When do those stay less than 0.5? The reason we have to put it in parentheses is because we're subtracting that whole linear function. And because it's absolute value, we could have done it in either order. We could have done the linear approximation first minus our function if we wanted. And we're just going to do this in the calculator now. So we'll go to a graphs page. We'll put the left side in F1 and the right side in F2. And we'll see when does that absolute value stay below 0.5. Now, because we want to stay below 0.5 right from the start, I'm going to switch our y max to something like 1. So it's a little bit easier to see. And I'll switch the y min as well. You can do that just by double clicking. We'll switch it maybe to -1. Okay, just so the window is a little bit closer to what we want to see. Hit your tab to graph. If you're not sure where absolute value is, go next to the book, and it's the second one down on the left. In our absolute value, we'll do our square root of x plus 3. Minus, make sure you put in parentheses. We've got x over 4. Plus 7/4. Okay, and that's the absolute value of that. And then we'll also graph, we wanted that to stay below 0.5, so we'll just graph y equals 0.5. And we want to see for what x values is it staying below that. So we'll find our intersection points. Go to Menu, Analyze Graph, Intersection. Your first curve. And your second. Okay, we'll go lower bound again and upper bound. Oops. So we got about negative 2.65 and 8.65 is the x values it must stay between. So as long as x is between about negative 2.656 and positive 8.6568 or so, okay, when x is between those, that is when we stay within 0.5, representing a good linear approximation. Now, we could switch this and do it, when will it be 0.1? So we could do the same thing and just say less than 0.1. And notice it gives us one of our intersection points is negative 1.12 now. And the other we've got about 3.92 or so. So if we were doing 0.1, our x's would have to stay between about negative 1.12, and it would have to stay less than about 3.92 or so. Okay, so that's just basically defining how good is good enough, basically, for our approximation. So one last example. We want to verify that the linearization, so that's just saying your linear approximation equation of our function at a equals 0 is really just the function y equals x. So we're calling it L of x equals x. So if we're doing a equals 0, first see what's the y value that goes with that. Well, when we put 0 in for x, sine of 0 is just 0. So we're working with the point 0, 0. When we do our derivative, f prime of x is equal to cos x, and we want to find our derivative at 0. Well, cos of 0 is just equal to 1. So we'll have y minus 0 equals a slope of 1 times x minus 0. That's just y equals 1 times x minus 0, which is just x, and that's essentially what we had here. Again, you can either call it y, or if you want to put the L of x in, that's fine as well. So this just shows that really close to 0, y equals x is a good approximation of sine. That's all for today's video. We'll see you next class period.